Okay, here's a short or brief qualitative lecture covering seismic waves. Okay, first of all, there are 4 different types of seismic waves. I encourage you, by the way, to also pause this video in a few minutes after I give you a brief explanation of each, and then take a look at one of my screencasting videos that I've posted for you in today's folder, where I show you some animations of the different types of seismic waves. Okay, first of all, within the volume of the Earth itself, there are 2 types of seismic waves. P waves, where the P stands for primary. These waves are longitudinal, and S waves, where the S stands for secondary. These are transverse. So there are 4 major types. Okay, first, within the Earth's volume. So these are 3-dimensional waves for that reason. You have, first of all, what are referred to as P waves, where the P stands for primary. These are longitudinal. And then S waves, where the S stands for secondary. These are transverse. Okay, because the P waves are longitudinal, they propagate faster than the S waves, which are transverse. So P waves are faster than S waves. And overall, the speeds of seismic waves is usually measured in terms of kilometers per second, because the seismic waves are passing through very rigid material. Remember, basically, the more rigid the medium, the faster the propagation of the waves themselves. Okay, now, when these waves then reach the surface, they then propagate along the surface of the Earth in 2 different ways. There's, first of all, what is referred to as an R wave. It's named after somebody. It's called a Rayleigh wave. And a Rayleigh wave is where the propagation along the surface of the Earth is much like that of an ocean wave. So just imagine, for example, the ground rippling towards you like so in this manner as the wave propagates along the surface of the Earth. This has never been photographed before, because you would basically have to be at the right place at the right time to see it, but eyewitness accounts have been recorded that have had people describe, for example, the propagation of these waves during extremely violent earthquakes. Okay, the actual wave motion itself is similar to that of an ocean wave. That is, each little portion of the surface of the Earth kind of moves in a little circle like so as the wave propagates. However, most of you probably have felt at one time or another during an earthquake the second type of wave that propagates along the surface of the Earth. This is called an L wave. It's named after somebody. It's also referred to as a love wave for that reason. In this particular case, this is like the familiar sideways swaying motion that you sometimes may feel during an earthquake event. Basically, the surface of the Earth is kind of rippling in this manner like so as the wave propagates. Okay, I invite you at this point to go ahead and pause this film and then take a look at my little screencast where I show you the animations of the different types of seismic waves. Okay, let me do some erasing here. Okay, now let me distinguish between what is known as the focus and perhaps what you're more familiar with, what is referred to as the epicenter during an earthquake event, a seismic event of some sort. Okay, this is going to somewhat challenge my artistic skills here. What I'm going to draw here is a 3-dimensional volume of the Earth, like so. So here's the Earth's interior, so we're going down in depth in this direction. And then right here we'll say is the surface of the Earth. Okay, and then let's say that right here is the point where the waves then propagate from. like you have, for example, some sort of slippage associated with tectonic plates and so on and so forth. Let's say that happens here at this depth. If you're talking about a transform fault, which is what we have here, for example, in Southern California with the San Andreas Fault, as, for example, the Pacific Plate and the North American Plate grind against each other sideways, the depth of the focus is usually a couple of kilometers. However, if you're talking about a convergent plate boundary, such as a subduction zone where one plate is subsiding underneath another, or subducting rather, underneath another, then the depth associated with those earthquakes is a little bit deeper, somewhere in the neighborhood of 10 kilometers or so. At any rate, however, the point where the slippage occurs, where the waves propagate from, that's referred to as the focus. Okay, so the focus is the point of origin of the seismic waves. Okay, and then the seismic waves would then propagate outwards in 3 dimensions spherically from that point. Okay, I'm going to go ahead and draw a couple of different seismic waves here. I'm going to give myself some room on my diagram as I do. Let's say right here is a wave crest like so. And then let's say that right here is another wave crest, like so. And notice with my second wave crest that I now have it intersecting the surface of the Earth. Okay, now directly above the focus on the surface of the Earth, that point right there is the epicenter. So the epicenter is the point on the surface of the Earth. Directly above the focus. So then therefore, when the 3-dimensional seismic waves from the Earth's interior, P and S waves for example, reach the surface of the Earth, they then propagate as R and L waves, and they do so in a circular manner, 2-dimensionally, from this point. So then therefore, this wave crest, for example, right here, this would then propagate in a circular manner like so, away from the epicenter like so in 2 dimensions. And once again, the epicenter here is this point on the surface of the Earth directly above the focus. So then therefore, it looks like the seismic waves are coming from that location, the epicenter on the surface of the Earth. But once again, the actual point of origin where the actual slippage occurs with tectonic plates and so on and so forth, that's down here at the focus within the Earth's interior. Let me go ahead and draw another wave crest, for example, like so. So then these guys here on the surface of the Earth, those guys right there are circular in nature. So you have circular waves here, and then these guys down here are spherical. Okay, let me briefly describe to you how we actually detect seismic waves. It's fairly easy to do. Basically, what we do is we employ a simple device that is referred to as a seismometer. So a seismometer is actually nothing more than a mass, for example, right here, that's attached to a spring. And then I have right here, for example, one of my markers, and imagine that the marker here is taped or attached to the seismometer in some manner. And then you have a piece of paper, a graph paper, that is basically scrolling in this direction like so as time goes on. So then therefore, when a seismic wave reaches the location of the seismometer, basically the mass on the spring jiggles a little bit. And when it does, then the marker itself then draws on the piece of paper, which is scrolling in this direction, producing what is called a seismogram, sometimes called a seismograph. You've seen these before, for example, because every time that we have an earthquake here in Southern California, invariably on the news, they're going to show the seismograms themselves. So the seismogram is nothing more than a piece of paper, a graph paper, that is produced here by this mass attached to the spring, which then basically jiggles as the seismic wave reaches its location. Let's say, for example, that a seismometer records the location, or rather the arrival, that is, of a P wave and an S wave. Okay, so a seismometer is basically a mass attached to a spring. oscillates when a seismic wave arrives. This then produces a seismogram. Okay, here's what a typical seismogram looks like. Okay, once again, let me just visualize it here in terms of the detection of a P wave and an S wave. When an actual earthquake occurs, what arrives first at the seismometer is the P wave. And the reason for that is because the P wave, which is longitudinal, propagates at a greater speed than the S wave, which is transverse. So then therefore, on a typical seismogram, you're going to see very distinctly two waveforms, like so, and like so. So then therefore, imagine that right over here is where the marker is at this moment. This then means that right here is the direction of the scrolling paper. And then therefore over here to the left-hand side, this is the past. So basically what we're recording here is the position of our oscillator as a function of time. And if the marker is right here, this is then therefore the present. Okay, right here, for example, marks the arrival of the P wave. Right here, for example, marks the arrival of the S wave. Okay, the difference between the two, that is the difference in the arrival times, is referred to as the lag time. The lag time increases the further that the seismometer is from the epicenter. Okay, the reason for that is the following graph. Okay, this graph plots the following. First of all, here on the vertical axis is time, and then over here on the horizontal axis is the distance from the epicenter. Okay, on this graph then, we can graph out then, for example, the propagation of the S wave and the P wave. The P wave travels faster. So then therefore there is a curve associated with the P wave that looks like this. Notice that it reaches a large distance from the epicenter in a relatively short amount of time. However, the curve for the S wave on this graph looks instead like this. So in other words, it takes a greater amount of time here, for example, for the S wave to propagate the same distance as the P wave. The difference between these two red curves, like so on the graph, that then corresponds to the lag time. So the further that you are from the epicenter, the greater the lag time on the seismogram. Once again, that's explained here by this graph. If you essentially measure the lag time for at least 3 different seismometers for the same earthquake, you can then use some geometrical triangulation to determine exactly where the epicenter is. That's how they locate the epicenter during an actual earthquake event. If you do this in 3 dimensions with seismometers, for example, buried within the earth itself, you can then map out in 3 dimensions ultimately where the focus is located. So that's basically the importance of a seismometer and a seismogram, to locate, first of all, the epicenter itself, and then secondly, locate the focus. Okay, let me do some erasing here. Okay, moving on to a different topic, let me briefly describe to you the structure of the Earth's interior. Okay, so I'm sure you're aware from basic Earth science that the Earth's interior has the following layers. Okay, first of all, we have the upper layer of the Earth, which is the crust. There's actually two different types. There's oceanic crust and there's continental crust. Oceanic crust generally consists of minerals and rocks and so on and so forth that have a heavy metal content associated with them. This then means that they're denser than continental crust, which is mostly made out of silicates, rock-like minerals, for example, which are less dense than metal-rich minerals like what you have in oceanic crust. The gist of this then, therefore, is that the oceanic crust floats a little bit lower on the mantle, which is underneath the crust. Okay, so here's the crust, and as I said, there's two basic types, oceanic and continental, and then we have underneath that the Earth's mantle, like so. By the way, the reason why the mantle is called the mantle is for the following. What do you have with a mantle at your house? Well, you put things on top of it, right? Same thing here, the crust is on top of the mantle. So that's why the mantle is called the mantle. I know that seems a little bit silly, but that's just the way it is. Okay, now the upper portion of the mantle is solid. Underneath that, there's like a plastic layer associated with it called the asthenosphere, and then it basically becomes a solid once again as you reach the boundary here between the mantle and the Earth's outer core. Okay, the portion of the upper mantle along with the crust is broken up like so into about 24 or so tectonic plates. So that's what I'm drawing here like so in red. So the tectonic plates are not just the crust itself, but also the upper portion of the mantle, which is solid. The crust and the upper portion of the mantle, which is solid, is sometimes referred to as the lithosphere. And then the lithosphere is basically slowly moving around on the plastic portion of the mantle underneath it, called the asthenosphere. And then that motion then describes all the geology that we see here at the surface of the Earth, and most of the geology that we do see takes place at the boundaries of the tectonic plates, etc., etc. Okay, and then underneath the mantle is the Earth's outer core, and then we have the inner core. Okay, the outer core and inner core are denser than the mantle, so then therefore they're deeper in the Earth's interior. And essentially the Earth's outer core and inner core is made of metallic type of materials, primarily iron and nickel and other very heavy, dense metals. Okay, the outer core is actually at a lower temperature than the inner core. The inner core is actually hotter than the outer core. The outer core, however, is a liquid layer, and the inner core is a solid. So how could the inner core, which is basically made of the same materials as the outer core, be a solid if it's hotter than the outer core? Well, it's under an extreme amount of pressure. Basically, in general, as you go down into the Earth's interior, three things increase: temperature, pressure, and density. By the time that you get to the location of the inner core, the pressure there is so large, even though the inner core is hotter than the outer core, that the pressure itself basically freezes it in place. That's why, for example, the inner core is a solid. We sometimes refer to this process, by the way, as pressure freezing. Okay, now we know essentially a huge amount of detail about the structure of the Earth's interior, where the boundaries between the different layers are, and all sorts of details about their physical properties. Temperature, pressure, density, what the different layers are made of, etc., etc. So the question then becomes is, well, how do we know all of this? You can't dig down into the Earth itself and actually look to find the different boundaries between the layers, because as you dig really deep holes, the pressure increases enormously. The deepest mines that have ever been dug, basically in the middle of continental crust, where the crust is the lightest, well, the deepest mines that have ever been dug are somewhere in the neighborhood of a few miles or so. The reason why it's difficult to dig really deep holes is because the pressure increases as you go downwards. Basically, your mine shaft wants to snap shut. There have been some attempts to drill through the oceanic crust at its thinnest locations to actually reach physically the mantle, but as far as I know, all such attempts have failed. So then therefore, if we can't actually look directly at these layers, how do we know that the layers are there? How do we know all the details of their physical properties and so on? Well, what we do is we actually do look at the layers, but we don't look at the layers by using visible light, like I'm looking around the classroom right now. Instead, we look at the layers by using seismic waves. So we know all of the details of the layers. In other words, where the boundaries are located. The physical properties, physical and chemical, let me say that as well. Physical and chemical properties. Etc. by looking at the layers with seismic waves. So as seismic waves pass through the Earth's interior, you could, by the way, produce seismic waves artificially by detonating an explosion at the surface of the Earth. Or, of course, you can look at all the details of seismic waves as they propagate from earthquake events. And then, by the way, there is this huge worldwide network of seismometers that's been in place since the 1940s. The original reason why the United States placed seismometers all around the world is because early on they wanted to monitor nuclear weapons tests from the former Soviet Union. One side benefit, of course, from this worldwide network of seismometers is it led to our understanding of plate tectonics, our understanding of the structure of the Earth's interior, et cetera, et cetera. So modern geology more or less begins in the 1940s with this worldwide network of seismometers that was placed. At any rate, however, once again, we know all the details of the layers, et cetera, by looking at the layers with seismic waves. So here's a basic description of that. So let me draw here, first of all, a very simple Earth. Let me say that I draw an Earth here that just consists of a single layer and is completely uniform. So then therefore it just looks like this. Like so, and then boom, let's say that we then have a source of seismic waves which then propagate through this Earth. Well, if the Earth itself is completely uniform, then the waves will not refract or reflect off of anything. They'll basically just propagate in straight lines, for example, like so. Here, here, and here, and then we could detect the arrival of the seismic waves, for example, here at the surface of the Earth by using the seismometers that I mentioned a little while ago. Okay, now, secondly, let's say that I have an Earth that once again consists of just a single layer, but now let's say that the density or the temperature or the pressure associated with that layer changes as you go down into the Earth's interior. By changing properties of the medium in this manner, this then means that the seismic waves are going to start to refract, like water waves, for example, refract when they slow down or speed up. Same thing happens here with seismic waves. So here's now my second Earth. And then boom, once again we have the production of seismic waves. And then I'm just going to draw two in this case. Those seismic waves, as they propagate through the Earth's interior, will then change direction, like so, as the physical properties of that layer changes. The waves themselves will refract. So then therefore you would detect the arrival of those seismic waves here and here at these locations, as opposed to the other locations in my previous diagram. Okay, let me go ahead now and draw another type of Earth here, this one a little bit more complicated. Let's say that in this case, I draw an Earth here that consists of two layers. Here, and here, and then boom, once again, we then have the production of some seismic waves. In this case, I'm just going to draw one. So let's say that seismic wave is propagating through this layer of the Earth, and it now encounters this boundary. Remember what happens, for example, when you take two springs and attach them together. You get a transmission into the second spring. In this case, it will be a refraction into the second layer, like so. But then you also have a reflection into the first spring, if you remember. Same thing here. You get a reflection off this layer, like so. So then, by looking at the details of these reflections, for example, off the boundaries themselves, and let me go ahead and refract this back into the original layer like this. And then looking at the details of the refractions here, by noting the arrival of the seismic waves at the locations of your seismometers, then you can mathematically work out all the details of where the boundaries between the layers are located, what their physical properties are, et cetera, et cetera. So we're basically looking at the Earth's interior, not by using light, as I once again look around the room, but instead by using seismic waves. That's the basic idea. This is a whole sub-branch of geology that's sometimes referred to as seismology. It's also sometimes referred to as geophysics. Now, I posted for you a nice screencast here, my own simple narration of a nice animation that shows a model of the propagation of seismic waves through the Earth's interior. I invite you to take a look at that screencast. One last thing, however, before I conclude today's lecture on seismic waves, and that has to do with the outer core. Okay, as I mentioned earlier, we know that the outer core is a liquid as opposed to a solid, and there are two reasons for that. Number one, the motion of that molten material, that molten metal within the outer core, that's the source of the production of the Earth's magnetic field. So we know it's there for that reason. But we also know it's there for the following. Okay, let me just resketch here briefly. Okay, now let me say specifically that this right here is the Earth's outer core, which is liquid. And then let's say that I have the production, once again, of seismic waves, P and S waves, like so at this location. Okay, let me just go ahead and draw right here the P wave in red. It then encounters this boundary and it then refracts into the outer core, like so. Okay, let me go ahead, however, in purple, say, and draw the S wave, like this. The S wave does not propagate into the outer core. And the reason for that is because transverse waves do not propagate through liquids. This then means that the S wave, its energy damps out as heat immediately. So when we send S waves, for example, through the Earth's interior, out here in this direction like so, on this side of the Earth, there is a shadow zone, as it's referred to as. In other words, no S waves reach this location here to here, and the reason for that is because those transverse S waves have damped out as they tried, if you will, to propagate from the mantle to the Earth's outer core. So that's another reason why we know that the outer core is a liquid, because S waves do not propagate through it, okay? All right, so that concludes this brief qualitative lecture here on seismic waves. Make sure, however, that you take a look at all of the stuff that is in today's folder. Today's shirt is grave. See ya.